call from Zoom to see if they can hear us? Okay.
They can hear us. We check.
Okay, so good afternoon to all of you. I'm very happy to be here. I'm Oded Margalit from Ben-Gurion University, Computer Science and Next Silicon. And I'm going to talk today about our CPU, the data flow. I'll give you some details and how it can connect to your work. But first, I'll talk about myself a little. This is a very, I like it, caricature XKCD about the purity of research things. So the sociologists are here on the left, and the psychologists are laughing at them. Sociology is just applied psychology, that's all. And then the biologist holding an octopus or something says that psychology is just applied biology, and biology is just applied chemistry, and chemistry is just applied physics. And it's very nice to be on the top of the chain, very, very happy. And then far, far, far away, mathematician, I never saw you guys. So I'm, as you can guess from this caricature, I'm a mathematician. My first degree was pure mathematics, and I like to talk about things that are interesting and look on the applied stuff as a second grade. I hope you won't understand it from my talk, but I think that engineering is okay. The Venn diagram. I like splitting the words into 8 parts, and let's do it with the government, the industry, and the academia. The government is responsible for mainly foreign policy, defense, education, things like that, but it does other things. The academia is focusing on basic research, training the next generation of students, and other things. And the industry is talking about money, getting financial gain. But, as you can see in the Venn diagram, there are intersections. So, for example, the Emirates government, Dubai Free Zone, has created a special place using the government power to bring companies into Dubai. And this is the intersection between government and industry. The Malad, המועצה להשכלה גבוהה, Council of Higher Education, is a governmental body that's focused on academic research, and MAFAT, the Defense Research and Development. In the Hebrew version of this slide, the name R&D, the D is development, and it's written the other way around, so the D here is development. So research is part of the academia, and development is touching the industry as well. And of course, you can look on places like Bell Labs, IBM Research, and other big places like that, which are industrial companies, and they have some interesting research. Meta, Google, other things like that. And this very long story is just to explain what I'm going to talk about today. The two logos here are, from the left is the IIA, the Israeli Innovation Authority, רשות החדשנות, and the other logo is Next Silicon, the company that I'm working at. I'm the head scientist there. And what we have is we won a tender for 30 million shekels to create the Israeli HPC, High Performance Computing Lab. And I'll explain a little about that. But this lab is actually at the intersection. Every time you draw a Venn diagram, you always put the good stuff in the middle. At the intersection of government, IIA, industry, like silicon, and I'd like to argue research and academia, and that's why I'm here. So this is the lab, and now a little about our solution. So we have a line from left, general purpose, and to the right, special purpose. On the left, there is a CPU, Central Processing Unit, Intel, and others. They have amazing capabilities, much better than what they had a few decades ago, but still, talking in HPC terms, they are rather limited. The GPU, Graphic Processor Unit, if you want to multiply matrices and do other stuff, you can do much faster and better. It has some porting effort. Not everything works out of the box on GPU. Something, not always you get the high performance, but it is usually faster. Deep learning, for example, are running on GPUs. On the right side, you have ASIC, application-specific integrated component, something that you build for a very specific use case. You can, for example, a problem that 5 years ago was considered interesting, protein folding. You could do it on CPU, GPU, and all kinds of machines, but if you want really high performance, you can build a specific hardware for that. The problem there is, first of all, it costs $100 million and a few years until you get the first sample. And it's very specific to a specific problem. So, for example, a lot of people are talking today about accelerating AI. And you can build an ASIC which is tailor-made for some kind of DNA, but few years from now, until you get the first sample, maybe the algorithm will change and you'll get a very fast way of solving yesterday's problem. So that's the problem with ASIC. There is another thing, the FPGA, Field Programmable Gate Array. It's nice, highly programmable. You can run things very efficiently on it, but still, it costs quite a lot to develop. You have to write your problems as a series of lookup tables, functions from 5 bits to 2. It's not that easy. What I would like to have is something that you can take your source code in C or in COBOL or Fortran or whatever, don't change it at all, and just run it and get the high performance without the porting cost. And of course, our reconfigurable hardware is just like that. You can take the source code. I will explain in the next slide a little bit about it, and run it on our hardware and get the performance. For example, those of you who are using Berkeley GW or other applications, you can just out of the box take it and run it and get the speed up. Any questions? Okay. So what is our reconfigurable hardware? You take a program. This, for example, is a very short program. If you haven't noticed from the beginning, I have readers. What does this program do? You have a hint, a comment, the first line is the answer. You take a series of 32 bits and reverse them. It's very easy to do in hardware, just do 32 wires in a blink of an eye, you switch to bits, but in software, it's not that easy. This is a nice way to do it. You take the even bits and the odd bits and switch them, and then you take pairs and fourths and etc. And trust me, it's reverse the bits. That's just a sample program. You take this program written in C, you translate it to a graph, computation graph. The source X is on the top and 14 layers down. The output inverted X is the switch, and you can see the translation. We do it automatically. Translate high-level programs into some intermediate code, and then create a computation graph. We take this graph and embed it into our hardware. Meaning that now we have, this is the hardware, and we have each block here can perform a simple instruction, and we embed these functions such that the input here will go to this shift left, shift right, etc. Functions. And once we'll get an input, 14 steps later, we'll get the output. But if you get thousands inputs, then 1,014 steps later, you get 1,000 output. So you can parallelize it very fast. And not only that, you can also parallelize it much better. What we do is take the software, compute the graph, embed it to the hardware, run it on the hardware, and then get, this is called the projection, and then get telemetry. What parts of the program runs how many times. And if we realize that this part is running million times, then we duplicate it thousands, tens of thousands of times and run it in parallel. And now we have a better projection that can project, use the hardware more efficiently. And we do it again and again. And after a while, we get a very, very efficient program. We can also realize that some part of the code are rare cases. Let's say, for example, that you are dividing two vectors element-wise. So there is an if. If the denominator is 0, then do some strange stuff. And the hardware see that this if is almost never taken. So it throws it away and says, I'll compute in the fast hardware only the path that runs most of the time. And if I'll get 0, I'll talk to the host, pay some precious microseconds to take care of this case, but it will be much better because handling the rare cases in our hardware is not the efficient use of the hardware. And again, the nice stuff is that all this process is completely automatic, at least it should be, and take the source code that nobody touched 20 years and get a running application. Even more than that, let's say that your application is a video compression. And the video compression has different ways of handling smooth scenery view versus explosions. It's different parts of the algorithm. If the movie has half an hour of long shots, then the hardware will gradually be more optimized to compress this kind of video. And then let's say that the movie A ends and the same compressor gets a feed of some, yesterday I saw, how do you call it? Fast and Furious 10, a lot of explosions, then automatically the hardware will reconfigure itself to be more suited to your needs. You don't have to, like in CUDA GPU, or wait a few years for the next ASIC to support it. You get it for free. Okay, the last two slides are the main part of the talk. The first one is what you can do for us. The second is what we can do for you.
I ask a question?
Yes, sure.
For the previous slide, how long it takes to reach the optimized level when I switch the task? How fast?
It's God is in the details, but it should take seconds, maybe more than that. It depends. It's like כמה עולה חליפה ליתום. But it's not days or hours, and still it's not nanoseconds. You don't get it immediately. You have to reprogram hardware, it takes time.
How do you reprogram the hardware? How's it physically done, or you will explain it later?
No, thank you for the question. The hardware is an ASIC designed by us, the Maverick chip, and it has interconnection to the outer world, the host, and you can like FPGA, you can program it. FPGA takes might take even minutes to reprogram. We're faster than that, but you program it, and then automatically the telemetry comes for free because when the hardware runs, it has this. We paid some silicon area to have the telemetry and send it to the host, and then we can reprogram it. We can even do it inside the same job if needed. Okay, so what you can do for us, meaning what types of academic research areas are we interested in? So first of all, compilers. This is the logo of the MLIR, the Multi-Language Intermediate Representation. A very nice project that takes dozens of computer languages and translates them all into a single common IR, intermediate representation, that we work on. So we don't have to write again and again for C++ and etc. So if you are interested in computer science, writing compilers, software development, that's one area. Another area are algorithms. I said that we are oblivious to the software, throw on us whatever you want and we'll handle it. It's the wishful thinking, it's not exactly that. In some cases, some algorithms are better for our hardware than others. For example, those who are inversely parallel are very easy to run on the hardware, and those who are serial in nature, we find it hard to use the algorithm, the hardware. So for example, graph algorithms are a case where the GPU are not well suited. The random access of following the edges in the graph doesn't play nicely with the GPU. CPU are slow, and we claim that we are better. We can efficiently use our hardware and get a very nice improvement. So one of the projects that currently we are doing is a joint project with NJIT, the New Jersey Institute of Technology, and BGU, Ben-Gurion University, and Silicon, to compare different GNN, graph network, neural networks, algorithms on several hardware configurations, CPU, GPU, and data flow, our solution. So that's another research area if you want to investigate specific algorithms. Optimizations, and again, I can't resist throwing in a riddle. This is actually, if you want to solve the riddle, don't look at it, this is the solution. How do you build a 3 gates inverter using only 2 NOT and 100 of AND and OR gates? You can't build a NOT from AND and OR because AND and OR are monotone, so you can only build the transitive closure of AND and NOT is all the monotone circuits, and the NOT is not monotone. So you can't create an inverter from AND and OR. But if you have an inverter, or let's say 2 inverters, then you can create a third one. How? If you want to cheat, this is the solution. I chose it because I played with this riddle, wrote it in VHDL, Verilog, and it's actually optimized it out to 3 NOT gates. The software today is so powerful that it understood that this complicated function can be optimized and make it 3 NOT gates, destroying the riddle. And I gave it as an example because we are building hardware and we want to multiply numbers or compute the hyperbolic tangents as an activation function or whatever. And we want to do it as fast as possible. So we are also investigating how to optimize this next, hardware design. The next one is, so we want to optimize the things. For example, this is the hardware, this is the CPU, this is the card. You can put it in your computer and run faster. If you want to make the hardware run faster, what we do is support the libc, the system library of generic function, sinus, cosinus, exp, etc. And every gate that we can squeeze out of these generic functions is converted to a faster way of solving your problems. Building a chip is hard, it takes a lot of time, you make mistakes. To avoid mistakes, people are testing, fuzzing, running the system a lot of times, and doing also formal verification, trying to prove. If you remember, Intel paid $475 million for a bug in the floating point division at the first Pentium chip. And if you don't want to have such troubles, then you have to verify that what you do really works. So it's a complete area of research, how to verify things, how to test them. Sometimes we have a huge machine that can emulate 3% of our chip. So you can run on this machine and try to do before you get the first engineering samples of the chip. You can do a post-silicon verification. When you have the chip, you want to compute. So again, there are a lot of interesting research. And the last one is computational mathematics. This is a paper we wrote at the CSCML last year, a conference at Ben-Gurion University, the cybersecurity, machine learning, and cryptology. If you are researching any one of these research areas, you are invited to come to CSCML 2024 in December. So that's the first part. The first part is we are researching many things. We want to do it with the academia in Israel and abroad. If you're interested in any kind of research, come talk to me, we can do things together. And save the dates. We have a conference on December 16, our offices in Givatayim, the HPC and an AI technology conference. We'll have a few presentations about solutions and a few presentations about problems. For example, CFD, computational fluid dynamics, and others. That's the last slide. Okay, that's what you can do for us, what we are interested. What we can do for you is a few things. First of all, this is von Clausewitz. Those of you who don't know him, he said that computers are a mere continuation of mathematics with other means. If you have a problem and you are a mathematician, you try to prove, to solve, to find a way to solve it. If you can't, you run simulations. Those of you who don't recognize the quote, okay, let's ask,
it's no longer relevant. Well, the original one. If war is the continuation of diplomacy or the other way around?
Yes, yes. War is the continuation of diplomacy in other means.
But here, war is the continuation of war.
Yes. And same for computers. Now we are using computers to simulate computers, and we lost the original beauty of the mathematical questions. But if you need HPC, high performance computing, if you want to solve problems that need a lot of computing power, that's one way. If you're working on, or we recognize this nice guy, the COVID-17, you want to research protein folding or kinds of variants, mutations, etc., then biology. You can run biology problems on our machine. Chemistry, who recognizes this nice molecule? Hint, hint. Exactly. That's a caffeine molecule. IBM used a quantum computer to simulate the caffeine molecule, and they were very proud of it. Look how much computing power is needed for simulation that nature does in an instant. Just put the atoms where they want to go. And engineering. This is a hypersonic simulation. You have an airplane or a missile or whatever that is traveling through, let's say, air, and you simulate the fluid dynamics around it. As you can see, you have larger cells here because this is a simple, quiet area. Things are laminar and everything is smooth. You have a very, very small vertices, polygons here because this is the real tough, the shock waves and the problems. So running algorithms like that, if you have problems that need CPU, again, you can do it. And of course, the last one, the three dots. Anything else that you may think about in the, I haven't talked about. Questions?
Yeah. Like, it sounds that you engineered the new architecture using FPGA and stuff like this to...
FPGA-like.
FPGA,
it's not
you didn't invent a new way to program stuff, but maybe you did. But as you say, it's IC. So how do you convince that you will be relevant, your architecture, in a few years from now? Like,
okay, so I have two answers for that. The first one is the proof is on us. We are working with possible clients trying to port their problems. Some of them says, I don't really care, I have this program. If you run it cheaper than my existing solution, I'll buy yours. NVIDIA GPU are hard to get. If you get me a better supply date or better performance or less power, then great. So that's one way. And another way is, that's why I came here, is working with you to find the use cases. I have a very large hammer, I'm looking for names. If you have a problem, let's talk about it, see if you can do better. If so, great. If not, look for another problem. The IIA is also funding, and for the Israeli academia, it's 100% funding, so you can buy some time on our lab, run your programs on different hardware architecture, and at least the academic part will get fully funded once you get the red tape of applying for the grant. And again, it's, I find it fascinating, the journey. I can't prove that it will work. If I would, then it will be engineering and not research. Research is the possibility of failing, but I like the journey anyway. Yes.
I have a question regarding the optimization phase. Like you said, that you find some if statements that are corner cases that you don't get in and you're excluded. In the scenario where you put this ASIC into an SoC, you have some IPs that use that specific if statement or something like that. Do you have some back and forth afterwards, after you finish the project, that you need to regenerate it because you excluded some if that is important for some IP?
Yes, this slide.
Yeah, that's why.
This is, it looks linear, but it's never ending. You keep doing, and as I said, it's not only that you try to optimize the same program more and more, you can, and of course, if the program changes, this process is, will do it automatically. But also, if the program stays the same and the date changes, it will also adapt to that. That's, I hope okay. I think, yes.
Do you have examples how this compares to regular ways that people use primary schools, let's say on Intel CPUs?
I don't want to get into specific numbers, that's a problem of industry, but I'll try to answer it in a different way. Coming to somebody and say, I have a very nice solution, let's try it. If it's 10% faster, then you won't even look at me, because what I'm doing is comparing existing competitors to my future solution. And even if I'll give existing solution, the cost of moving into new hardware and the pain of doing things, sometimes it's fun, especially in the academia, but the industry, sometimes they don't want this pain of being the first one to do something. If you don't give him orders of magnitude better, let's say 5 or 10 times faster than competitors, then you won't get into the game. I hope it's okay. Thank you very much.
Okay, so the next part, we're connecting briefly. Okay, so we have Nir Alfasi. Now,
It was muted. I was sitting there with Zoom open, but probably when I connected to the HDMI, it suddenly. Yeah.
We have to use the microphone and the speaker.
Yeah, it was both muted.
okay, so Nir Alfasi from Quantum Machines.
Stop this show. Are you still sharing your screen? Maybe your computer is not completely off. But it looks like you're still sharing. Okay.
Okay, so Nir Alfasi from Quantum Machines will tell us about the other interesting center of quantum computing, computing center.
It's not there.
It will be there. It should be there.
Here maybe. Screen. Switch. This one?
Display setting in the middle of the top, and switch to the other.
This one there is.
I cannot go.
We should be able to make
Okay.
Ah,
There?
no, the top
pointer?
Okay. Sorry for the delay. Okay.
Great,
Pointer.
thank you. What's right there?
Working? Okay. Hopefully it will. Yeah. Okay, hi everyone. So first of all, thank you for the organizers, for Iban and Itzan and some other people I didn't meet for organizing it and inviting me. I gave a talk here exactly, I think, 5 years ago. I think also Amit invited me here. So we do my PhD in my postdoc. So it's great to be back. Yeah, so I'm going to talk about something which is kind of related to what Oded spoke about from the other side. I'm going to talk about how do we want to unlock the full potential of quantum computers at the newly built Israeli Quantum Computing Center, and one of the ways is connecting to an HPC center. My talk will be divided into two sections. The first one I will talk about QM, Quantum Machines, the company that I work for and the company that I was given the mandate to build the Israeli quantum computer. And it will be more of a, it will be more of a scientific talk a bit, just a little bit. And the second part is about the Israeli Quantum Computing Center that we're building, and I'm in charge of building actually. Yeah, it works. So yeah, just a few words. So when I go and speak in front of students, I like to share my story. So basically, the story of a quantum physicist in QM, because I will show you later, but QM has like over 40, I think over 50 already physics PhDs. So it's a kind of a common story for everyone. So I did my bachelor's and master's at TU. My bachelor was actually in mathematics and physics, but I chose the more applied direction, although I did my master's in theoretical physics. I did my PhD at the Technion. I worked on quantum sensing using NV centers coupled to superconducting devices. I then, after I gave my talk here, I moved to a postdoc position at QTech in TU Delft, where I worked on quantum memory based on rare earth ions. So there's a small leap to the side. And after working on quantum sensing and quantum memory, I am now working on, I'm now working on quantum computing. So here, up to 2 hours ago, there was an illustration of a fridge in QM's rack, but this is a true picture taken in the Israeli Quantum Computing Center. So now it's there, it's working. Some of you might recognize the OPXs. I know we have a few customers here in Weizmann, and obviously many of you will recognize the Blue Force fridge. And this is where I am now at QM, working on more on the quantum computing side. Although I still have a sweet spot for both sensing and memory. Okay, so about quantum machines. So quantum machines is an Israeli-based startup, started in 2018 by 3 PhD graduates of Weizmann Institute from the lab of AMOTech, and it has grown rapidly ever since, with over 250 projects, over 300 customers worldwide, including several here in Weizmann. We have over 160 employees worldwide, including a Dutch-based startup named QDev that Quantum Machines acquired 2 years ago. So we have offices in Israel, Stuttgart, US, Denmark, obviously. We have small office in Paris, etc. And we have many customers worldwide, both corporate, startup, national labs, like the Israeli Quantum Computing Center, and academic institutions. So the goal and the agenda of quantum machines is basically to accelerate the realization of these quantum computers. And we do it actually with our quantum control stack. So we know that there are many challenges lie across the entire stack. So when I'm talking about the quantum computing stack, talking obviously about the QPU, the control hardware, which is the QM product, we have the control software, and then we have the applications, right? So I'm not going to discuss the applications still. We're not there yet, and I'm going to leave the software to another talk maybe. And I think the main challenge remains the QPU. So the engineering of the QPU, the scaling of the QPU. But the question is, can we offload some of the challenges to the control hardware? And we believe that the answer is yes. And we divided the key aspects that will allow control hardware to carry some of the burden into 4. And I'm going to focus only on 2. So the one that I'm going to focus now is classical processing integration. Later, when we discuss the Israeli Quantum Computing Center, I will discuss a bit about scaling. So what do I mean when I'm talking about classical processing integration? So we know that quantum computers will revolutionize the world, etc., etc. I'm not going to tire you with all that great words. But people now understand that it cannot work without tight integration into classical processing units. And quantum machines have realized it back in 2018. And basically, we're looking at classical processing unit as an engine to help move faster. So not only quantum machines have thought about it, all of the big companies around the world, so IBM, Google, and Microsoft are also eyeing it. And in a benchmark that we did, we have a paper about it, and I will show you later. Basically, we consider this what we call the quantum classical loop. Okay? So we start with the quantum chip. It can be any quantum chip of your desire. And you want to do a quantum operation. For example, if you want to, I don't know, initialize, you want to drive it from an excited state to the ground state, or vice versa, whatever. So you do a quantum operation, and then you need to make a quantum measurement. You measure the state, for example. Again, I'm giving you the simplest example. And then there should be some classical chip doing some classical operation to realize what needs to be done, and then give back quantum operation to the quantum chip. So this is the entire quantum classical processing loop. And this is used for the example I gave you is active state preparation, for example. You want to actively, so before, for example, I don't think I have the examples here, but before the quantum controls that are FPGA based, people used to wait for thermal, for example, in superconducting qubits, for thermal initialization, for thermal relaxation. That is in the order of milliseconds. And for active state preparation, it can be in the order of tens of nanoseconds. So that's already 4 orders of magnitude. But it's also for things that are much more complicated, like quantum error correction and variational algorithms. You can see we go up the stack here. And we also divide, and we also divide the 3 operations that needs to be done into 3. So we have conditional operations, which is if else do something. Let's say if the state is 1 or if the state is 0, make a pipelines, etc. We have control flow, which is more for while loops, etc. And we have parameters updates. And these 3, each and every one of these operations has a different time delay, has a different time constant. And we call this entire thing the classical feedback latency. And now we divide this classical feedback latency into 3 regimes. The first regime is the QPU, we call it quantum real time, and basically the feedback latency has to be shorter than the QPU coherence time. This is, for example, for active state preparation. What you want to do is you want to read the state of the qubit, okay? You want to make a decision based on the state of the qubit. Let's say that it's 1. Now you want to make a pipeline to do active reset to bring it to the ground state, but you have to make it faster than the relaxation time, than the coherence time, sorry, not the relaxation time. So you know the state is still at 1, okay? So this is an example for a quantum real time. The feedback latency here must be very, very short. The second kind category is what we call system drift time. So everyone that has ever worked in the lab knows that there are drifts, for example, in the qubit frequency. So if you have, if you drive the qubit in a certain frequency, you want to make sure that it stays in that frequency. And if the temperature changes, for example, if the air condition turns on, if there is like 50 hertz, there are lots of things that can happen with a longer time scale, but you want to be able to correct your frequency, and this is an example for a correction. So you want to read the frequency and correct it in real time on the fly. You don't want to go into a memory, you want to do it in real time. That's the second category. And the third one is basically that you want your feedback latency to be shorter than the quantum computation time. So if the quantum computation time takes, I don't know, milliseconds, and then you have to run it on a classical hardware for 2 days, and you lost all your advantage. Doesn't make sense, right? So you need your class. So this is, for example, for quantum error correction. You want your classical code to be in the order of the quantum operation time. So we have published a paper. I think it's already published. It's here. It's on archive, where we map basically the feedback type and the regime timing, and we map what is needed to be done for each and every, let's say, I don't know if to call it application, but let's call it application in quantum computing. Okay, so as I told you, basically in 2009, we moved from the industry moved from AWG-based, memory-based instruments into an FPGA processor-based. So everything is done on the fly. And we have introduced the quantum orchestration platform, which is a processor-based approach to quantum control. So this is our OPX Plus. We now have a newer version, which I will show you later. It's called the OPX 1000. But basically, the OPX Plus it has an RF microwave front end, like every AWG or signal generator that you know. But it also has a pulse processing unit, which is basically the brain and the heart of this machine where the magic happens. And it's agnostic to any quantum device. It can be used for NV centers, it can be used for spin qubits, trapped ions, neutral atoms, and of course superconducting qubits. And above all that, we have QA, which is the intuitive quantum programming language by quantum machines. So by introducing 4 operations, we know we can fully control the system. The first one is we need to be able to do waveform generation. The waveform generation is fully parametered. Again, what does it mean? When I did my postdoc, I love giving personal examples. When I went to postdoc, we had an AWG, an amazing state-of-the-art AWG, $150,000. It was super good. But when I came there, people told me that yes, if you want to change your waveform, I was doing weird waveform, but if you want to change anything in the waveform, any parameter, you have to upload your waveform again. Because it had like 25 gigasamples per second, it took them about 40 minutes to upload a waveform. When I came there, I said it's crazy, and we worked hard and we reduced it to like 3 minutes. Okay? But that was the order of magnitude, or 1 minute, I don't remember. But you could do it, if you did it smart, you could do it in, I don't know, 1 minute. But here everything is fully parametric, so if you want to change the amplitude, it's on the fly. Everything it's in real time actually. The second thing that is very, very important in quantum computation is waveform acquisition. That fancy AWG could not read the state and act accordingly. So we did not have any feedback. So here you must have waveform acquisition and manipulation on the fly. The third thing is real-time processing, so you can do mathematical functions. You can do Fourier transform, you can do, I don't know, multiplication, squeezing, stretching, whatever you want in real time. And the third thing is that you need control flow, basically, of all these parameters. And if you multiply it by n, you can control n qubits. And with the OPX Plus, you could stack, I think maximum 13 OPX buses, which could give you 130 channels. So this was good for controlling about 30, 40 qubits maximum. And it's still great, and I think all of our customers have the OPX Plus, and it's working amazing, and also in the Israeli Quantum Computing Center, we also have the OPX Plus. So the heart of the quantum classical integration, I hope I convinced you that it lies in the control layer, but as I said, right now we can only get to about 30, 40 qubits, which is great for academia, it's great for small startup, but it's starting to be too small for what we want to achieve in quantum computing. So the second thing that we need to discuss is scale. So basically, the idea is that we want, maybe it's, I don't know where this picture taken, maybe it's here, right? I'm not sure. But we want to move basically from a lab controller to quantum data center infrastructure. And to be honest, we are thinking of it already for 2 years, I think it's even before. And we keep seeing that the entire world marches in that direction. So many, and it goes from the other way. So many HPC centers now bring quantum computers into the HPC center. We're building an HPC center, we're trying to build an HPC center around the quantum computer, but many HPC centers bring in quantum computers and basically believe in the idea that the data center also has like a CPU, GPU, DPU, and also a QPU. So this is why Quantum Machines announced the OPX 1000, and again, the main idea is, okay, so we also obviously improve the analog specs, and now it's more powerful, but the main idea is that it's scalable and it's HPC ready. So basically, we have taken a whole rack, and it's now in a 3U device. So this has 64 channels, and basically you can take a whole rack into a small device, and you can scale it up to, as it named suggests, around 1,000 qubits. Okay, so far I've talked about quantum machine, and I said we provide an entire HPC-ready control stack. We give the control software stack, which is our language quad. We give the room temperature controllers, and we also acquired, as I told you, a company called QLevel, which give you the cryogenic electronics solutions. We have also started a collaboration with NVIDIA, which is called DGX Quantum. Basically, we tightly integrate the OPX to NVIDIA's Grace Hopper. And this is an ongoing project already announced about a year ago by NVIDIA, and we expect it to be, I think, the IQCC. The IQCC will be the first place in the world to be using this DGX Quantum. But in the IQCC, what we add basically to this stack is also, not yet, wait for it. So, because of all of this, because of the HPC readiness, we have been selected to lead Israel's Quantum Computing Center, also by the Israel Innovation Authority, similar to Next Silicon, only we got 100 million shekels. And this will be open in Tel Aviv University. It's already open in Tel Aviv University. And this is an illustration. It's not that beautiful. And this is, I think I can promise that it will be the last illustration. This is how it looks right now. So this is only the lab. I didn't take a picture of it. I tried to take a nice picture, but it's just really hard with my phone camera. So this is just a picture of the lab as it is right now. But the center is much bigger. We have offices, we have working spaces for external users, we have 2 more labs. So this is just one part of it. Basically, we were selected, I think, 2 years ago, summer of 2022, and we started this project in the beginning of 2023. And only now, almost a year and a half later, we're actually running. It was a very significant effort to bring it up. So now it's the illustration. So far, this is QM control stack, and basically at the IQCC, we add also the QPUs to this to the offering. So again, there was an illustration here, and I changed it. This is a real picture that I took on my way out a few days ago. So basically, the idea is that we want to provide a different quantum computing experience by giving power to the users. So the main question that I keep getting asked is, what's the difference? I mean, why should I connect to the IQCC, and I will tell you in a bit what we offer, instead of going to IBM, instead of going to Bracket? And my answer is always, first of all, we're not trying to compete IBM, okay, because we will lose. That's not my main goal. But the idea is that we actually give power to the users. We give more lower level access, we give pulse level access, we give an HPC integrated into the systems, and I will shortly elaborate more on the advantages, but this is more actually for power users rather than, if you want to just run your algorithm on a 10 qubits device, then probably, or 40 qubits, but probably it's better for you to go to IBM. But if you want to do things that are more, if you want to control your algorithm better, you want to control your parameters, you want to do if it's optimal control, if it's optimal collection, then I think we are a better solution. So yeah, I'm going to talk a little bit about the architecture. So we have, for now, 3 platforms. The first one is superconducting qubits QPU, and I will elaborate on each and every one of those, but it's based on Quantware chip. Quantware is a Dutch-based company. We have a photonics QPU, which is delivered by Oka Computing. We have an open testbed, which is basically a fridge for rent, but it's a very this fridge is very well equipped. So I know fridge for rent. There are many of them, not many, but there are several of them around the world, and usually they give you a fridge with some wires and maybe a scope and a network analyzer. This is not the case here, and I will elaborate on it as well. And platform 4, I wanted to change this to be decided into coming soon, but we will have another quantum computing platform. So the idea is to have multiple quantum computing modalities under a single roof. Everything is controlled by our orchestration platform, including the hardware and the software. So you have a unified backend, you have a gate to pass compilers, so everything should look the same in the eyes of the user. And under the surface, we are doing we are making it work on all of the modalities, and also integrated with the TGX Quantum. All of this is integrated with a high-performance computing cluster, GPU-based. This is being integrated by AMOTech, which is a known European company. I'm sure Oded here knows that, probably. And it will be both. It will be both on-premise and over the cloud. Yeah, we'll have the cloud layer. I will not elaborate too much. We also have the user's development environment layer, which is comprised of our Qiskit SDK, so QM. Also, we will have a compiler to Qiskit if you prefer Qiskit. We have Classic in our, basically it's a collaboration. So we have Classic bringing their expertise in here, and also Oka software libraries, etc. And the users and applications. Just put here all the Israelis, universities, and Elbit, which is part of the collaboration. So these are the companies that are participating. At the beginning, it was supposed to be a consortium, but at the end, it's just quantum machine leading, and the companies are sort of vendors. Where Elbit is actually a user, and we are in close contact with them. Okay, so the first platform, again, there were illustrations here, and these are real pictures. The first platform is superconducting QPU. I call it the QM platform. Why is it the QM platform? We only bought the chip, which lies here. This is our product. It's called the QK64. And everything that you see here, we've done with our hands. And we chose the filters, we chose everything, basically the cables. It was a very significant work, and for those of you who work in the field, you know how hard it is, especially for 25 qubits, which means that we have over 50, 60 lines here. So we have so again, the chip is 25 superconducting qubits delivered by Quantware. We have a Blueforce XLD 1000 dilution fridge. It's integrated and built by us. It's scalable to up to 100 plus qubits. So it depends on the technology of the wiring is also advancing, and that will basically restricts us from putting more and more qubits. Because from quantum machines point of view, we can go to up to 1,000. It's controlled by Quantum Machines OPX Plus. You can see it here. This is our cluster, and everything here is connected and working actually. On this side, you can see the electronics rack where we have network analyzer, spectrum analyzer. We also have the DC source, which is called QDAC. It's also our product. We give remote access to, it's integrated with an HPC facility, which I will discuss soon. And we give remote access for users, so you can log in from your house. Once it's calibrated and operated, it's still in work in progress, so the lab is working, but the users cannot still gain access to the QPU. But once we have it, we can remotely access it. You will see all the parameters. You can run your algorithm. Same, I would say, it's the same user experience as IBM provides on a smaller scale, but with a deeper availability. And we give you pulse level and gate level access. Yeah, so Quantware is the first, basically I would give 2 words about Quantware. They're the first, I say, company to be selling superconducting quantum chips off the shelf. They sold the Soprano, it was the first commercially available superconducting QPU. We will have the Contralto, which is 25 qubits QPU, and planned for early 2025, we'll have the 10 or 64. It's not really 64 qubits QPU, but that's for a different discussion, but it's above 50 qubits. And we will have it in the Israel Quantum Computing Center next year. The second platform is the Photonics QPU. This is being delivered by Orca. The Orca has their PT series. It's a UK-based company in London. Basically, it's a boson sampler. For those of you who are familiar with the term, and I will shortly elaborate a little bit. So the Orca PT1, we had some issues bringing it because of the war in Israel, but it's actually now on the plane to Azerbaijan for some reason. I don't know why. And then it's coming here. It's a crazy story. But it is coming and it will be installed in the IQCC next week. It's upgradable and scalable. Again, one of the conditions that we put for vendors to sell us this kind of machines was that they are controlled by our OPX Plus. It has mainly 2 reasons. The first one is that we want to give the user experience, the same user experience for all devices. But I think that the main one is that we really believe in our control and in the OPX Plus. We really believe that it can do much better than any other device. Again, integrated with an HPC, so everything is the same as the superconducting. Here we leave pulse level access because it's not, you don't have gate-based. Yeah, I gave a webinar, we had a webinar, it's already a bit old. I think it's a few months ago, about hybrid quantum classical machine learning and with the photonic quantum processor. It was with the head of machine learning in Orca, and if you're interested, you can go on YouTube and watch it. Okay, so these are a few slides that I took from William's presentation at the webinar. So, what is a linear optical quantum processor? Basically, you send photons into a circuit, and measuring where they exit, it offers a simple near-term route to quantum advantage. It doesn't have universality, but the interference produces a quantum superposition. And the idea is that above 30, let's say, photons coming out, it's really hard to simulate on a laptop, and above 40, it's hard to simulate on an HPC. So if you go above 40, you already gain some quantum advantage. So you just sample the probability distribution that is given, and it is actually really, it's actually used, for example, for machine learning. So by measuring the probability distribution here. You can change where you started. And they show, if you go to the webinar, he shows some nice results that they have. It's not nearly competing classical computer yet, but it might in the near future, let's say, more nearer than superconducting qubits. So yeah, so here they use photons as qubits, so qubit is a two-level system and a qubit is a d-level system. So 3 photons here in 6 channels, it gives you 6 qubits with 4 levels. And the Orca PT series, it works with loops. So basically, you send photons from a single photon source into loops. Each and every loop has a beam splitter, and you can control this beam splitter. This is the controllable parameter, and then you measure your output. So the more loops you have, the more qubits you have, and you can always map this into this picture. But again, in Orca, we don't really have few photons going in. It's not really spatial multiplexing, rather time multiplexing. Okay. And the basic idea, we're starting with 2 loops, and basically the idea is that 3 loops can give you quantum advantage. Again, this is a big leap. It only sounds like you go from 2 to 3, but it's not that easy. Okay, yeah, so the applications are quantum simulation, graph problems. It's also for machine learning, but I'm not going to elaborate more. This is, I think, a very, very, very interesting platform that we have. We call it the test bed. So again, you can see this is another OPX rack. You can tell because it doesn't have the same connection as we've seen before, so I'm not fooling you. This is an LD fridge. It's an LD fridge with a fast sample exchange. Fast sample exchanger is a bottom loader, for those of you who know. You can exchange sample in about 8 hours instead of 4 days. And this is here, this model right here. Again, I don't know if you can see, but it is fully wired. Okay, so we have all of the wiring inside. It's not just, it's really the state-of-the-art machine. We have all of QM's amazing products, if it's OPX, Octave, and QDAC, etc. Highly customizable. You can choose whatever you want to put in. It's suitable for multiple QPU platforms. The idea is basically bring your own hardware. You fabricated a qubit, you want to put it in, no problem, you can bring it. You want to test a filter, and no problem, you can test your filter, and if you want, we can also put a superconducting chip for you. Right? We have a superconducting QPU, we have 3 contraltos, which are starting from Quantor. We can put one in, and you can test a filter with a QPU. You can test 2PA, if you know what it is, amplifiers, whatever you want. And yeah, designed for testing quantum hardware, and it's basically kind of aimed to serve the Israeli ecosystem. So it's true that in Europe there are centers and people from Germany travel to Netherlands, and people from Denmark. My colleagues from Denmark actually went to London 2 weeks ago for such a fridge. But you know, when you come to Israel, it's a bit, I would say, a harder task. So we believe it's aimed to serve the Israeli ecosystem, and it's made for both academia and small startups. Yes, and again, it's integrated with an HPC facility. Yeah, this is again, I had an illustration here, but this is actually the NVIDIA, it's A100 or something. So we have 8, right? Yeah, so I'm not in charge of the HPC facility, as you can realize, it's my colleague. We have an on-premise GPU-based HPC cluster. It's integrated to multiple QPUs. So everything you run, you can run your calculations either on the OPX, if it's short ones, or on the HPC cluster. The idea is that you log into our user portal, which I didn't give a link to, but we have a user, we have a website now. So you can log in, you can say, okay, I want 10 minutes of QPU, 1 hour, 2 hours of GPU, 1 hour of CPU, etc. And AMOTech basically make it happen. Combined with DGX Quantum and allows advanced error correction algorithms and more. Yeah, so this is basically, I'm coming to an end now, and these are the pillars that we're looking to deliver through the IQCC services. Basically, we want to bring a quantum academy. So this is one of the things that we are collaborating with. I told you it's, maybe I didn't say it, but the IQCC is now open in the Tel Aviv University, or near to Tel Aviv University. And one of the collaborations that we're having with Tel Aviv University is about education. So if you have a quantum applications course, you will run your homework on the IQCC and not on IBM, for example. And we want to do workshops, summer school, anything, and we're obviously not limiting ourselves to Tel Aviv University, but also to Weizmann or any other university worldwide. So we want to kind of create a Q Academy, an incubator for quantum startups in Israel. We have an open space for external users. We thought about even leasing part of our lab to external companies, external startups, so they can start. Right? If you, let's say that you're opening your own company, you want to build, I don't know, you have a great idea, but it took us more than a year to build this facility. If you're a new startup without money, like we got, it will take you more than a year, so you can start by using it, and I'm sure the Israeli Innovation Authority will be happy to assist. And obviously give cloud services, as I said before. Another goal, this is one, is for the testbed, is basically technology validation. You have something that so many companies worldwide, they create filters, and now they're starting to, people buy, so I know for a fact that people start buying, so for example, filters and amplifiers from companies that build their filters for NASA projects. And now someone tried it once in his fridge, and now everybody knows, and it's now quantum filter, although it's not intended to. So we can do this validation. Yeah, so with that I will finish basically our goals to accelerate practical quantum computing, to develop a well-educated and well-trained workforce, and we want to basically place Israel at the forefront of quantum innovation. I believe we're still really, really far from this. Everyone believes that Israel is like leading, I don't know, in some research and science, and then you go to postdoc and then you understand we're not. So I think this is very, very important, because I think we're lagging behind, especially in quantum. Obviously we cannot compete with the money that has been spent on quantum innovation worldwide, but we have the Jewish brain or whatever, the Israeli brain, I would say. Yeah, so thank you very much. And we're also looking for collaborations. You can contact me if you're interested. Now it's your turn.
Is there a place to see all the, you said that you picked all the cables, the filters and everything, is there a place to see what exactly you have in the fridge? Like if I want, as a customer, to actually use the fridge, I want to know what's inside.
Yes, so it's a very good question. The idea is that, first of all, everything that I did not emphasize it, but one of the also the benefits that we give is that there are, and one of the actually the requirements from the Israel Innovation Authority is that there are no black boxes. You cannot have a black box. Everything is open, and we had people coming and watching, and you can come for a tour instead of our office. You can come there now. So the answer is yes. The problem is that I've put so much time on understanding what we want to put, so I still don't. I mean, yes, we will give you all the information you want about which, let's say, I would say the frequency of the filter. I don't know if I can give you the information of it. Maybe you I can, but like in general. You can come, okay, the answer is you can come to the QCC. I will show you around, you can look at anything you want and take anything, any information you want, okay? But the general question, if anyone from the world can know exactly what I put inside the fridge, I think the answer is, I mean, I don't know yet. You will know, they will know, we will give the information of the attenuations, the amplifications, the filtering, etc. But there is so much knowledge that has been acquired here in engineering that I don't want to know if I want to share it with a competing company that wants to build the same thing. You as a PhD student from Python probably, yes, sure, you can come. I had a PhD yesterday and I didn't stop him from seeing that.
Yeah, but as a user, if I'm
Yeah,
using
as a user,
the
it's
test bed,
transparent.
then I
It's
see
transparent to you. It's transparent to you, but there are so many. Only when you build a system like this, you understand how delicate it is, and it's not just okay, let's have a low pass at 8 gigahertz. It's not like that. So you will know we have a low pass at 8 gigahertz. Which low pass, I don't know it. Maybe you will know, maybe not.
For the testbed, we also need to bring our packaging, or in the QDevel, we also kind of just use the QDevel, or
So it's really, I
it
mean,
depends. Like then you have to.
yeah, no, you can bring your own packaging. You can bring your own fridge if you want, all right? You can bring whatever you want. We can offer packaging if you want. I think everything is a matter of funding. So, for example, packaging is not a problem. If you want to bring your own package, obviously you bring your own model, you can bring your own wire if you want. We can supply the wires. If you want us to supply you something, it's a matter of funding, right? If we get a grant, for example, for example, if you want a magnet, our fridge is magnet ready, but it doesn't have a magnet. So one of the things we thought of, okay, let's see how the market reacts. If we can get a grant for a joint project that requires a magnet, we'll buy it from grant money, for example. Right? So if you want something that we don't have, specific, I don't know, a current source that we don't own, if it's cheap, we get it. If it's expensive, we need to get some funding for it. But the idea is that you can bring whatever you want.
I'm trying to understand or to think how you can leverage traditional computer science education in academia to advance quantum computing in Israel. I wonder, if you think about sort of standard curriculum in undergraduate or master's degree computer science programs, how exactly do you how do you differentiate quantum computing from HPC in general? I mean, do you offer a course in quantum computing? Do you need physics prerequisites, which normally CS students don't have? How do you crack that?
I think it's a very good question. I think it's one that we now learn, right? So actually, I said I'm like the science lead, so there is like someone who's in charge of technology, and we're from the two sides. So I come from, I don't call it lab rat, right? I come from the lab. I want the internet, I connect it to the, I don't know. We're always fighting about it. No, he says, no, you have to go through the HPC system, you have to, it comes from cybersecurity, no, it's not security, I don't know. I just want to run the experiment. So, and now we're kind of coming together. So I'm learning more about him and he's learning more about our needs. And I think it's an open question. So for advanced, let's say, even bachelor degree, the answer is easy. If you go and run on Qiskit on IBM, you can run it here, right? Any algorithm, you can write even on Qiskit. We have the compiler down to Qua and to our quantum computer. And I think this is like the first step on how we join forces with academia. On education. If you ask about how do you combine the QPU into standard tens of decades of computers and supercomputers, etc. I think this is what we're trying to learn right now. This is what people around the world are trying to learn.
Okay, so thank you again, Nir, and thank you again. There's tons of food outside because we accepted 3 times of the people. So, wow, enjoy the food and hope to see you again next time.